Looking at example 3, we're asked to find and evaluate a limit. However, we have a couple of theorems that kind of help us out with that. In fact, the first one we've actually already gone ahead and used. So now this is actually just going to be like the formal definition for that theorem. And it pretty much just states that for any polynomial p of x and any real number a, if we have the limit as x approaches some a value of that polynomial function, then we can also just go ahead and throw that a into the actual function. So we would end up then with p of a. This is known to be that direct evaluation that we've been talking about. So again, there is the formal definition though that says that you can go ahead and throw that value into that polynomial. Now the second theorem is a little bit different. However, we've kind of seen a form of it in our properties with limits. So just kind of looking at it, it's got a little bit of a twist though. So suppose that you have some limit as x approaches a value of a function, and you know in fact it comes out to be some limit, and that limit exists. And there's some n that's a positive integer. There's a key that says that it's a positive integer. Then, if we have the limit as x approaches a of a function, but this function has a little bit of a twist, and it has an nth root. So that's really where we're starting to see our n now. Then there's a property, or this theorem says that we can go ahead, take our limit, throw him into that nth root right along with our function. So then we have the limit as x approaches that value a of the function. And then we have our nth root on the outside. So these are actually equivalent statements with one another. We can then go ahead and take that limit, connect it with our function, and then apply that nth root at the end. And so we end up then with the nth root of some limit. So that's where that definition, that theorem kind of helps us out. And that allows us to really then focus on the limit as x approaches a value of a function, and then not worry as much about that nth root. This is kind of similar to that power property that we saw previously. The only difference is that it's an nth root. It's still actually considered to be an exponent. It's just a fraction as an exponent instead of, like a higher degree than a fraction. Now, for example 3, how this is going to help us out is we don't really have to worry too much about this cube root. We can go ahead and use that theorem, throw in this limit in the inside. So when we do that, we end up with the cube root of the limit as x approaches 2 of 3x squared minus 2x which just simplifies out to be, now using that direct evaluation that we also talked about, we can go ahead and throw this value inside here. So we end up then with 3 times 2 squared minus 2 times 2. So we still have the cube root of 2 squared is 4 times 3 will give us 12 minus 4. So ultimately it looks like we are looking at the cube root of 8, and the cube root of 8 just simply comes out to be 2. So this limit will actually come out to be 2. Looking at 3b. 3b is actually a little tricky. Now, 3b, you may recall back to like algebra or algebra 2, where we actually saw like a bunch of square root items, and if you tried using direct evaluation right away, you would end up with that 0 over 0. So unfortunately that's out. But if you recall back to algebra 2, we talked about this thing called multiplying by the conjugate. So when we multiply by the conjugate, we end up with the square root of x plus 2 And then what goes on in between, instead of that minus, we're going to go ahead and apply a plus. So we're just basically swapping the sign there and then having a root 2. And then we'll just have the exact same thing on the bottom, square root of x plus 2 plus 2. Now I'd like to talk a moment about what this means. Essentially, we are taking this original function, multiplying it by, really anything divided by itself is just 1. So we're not actually changing this original function, we're just multiplying it by that fancy form of 1. So if you've had me in the past, you know that I've referenced that term foo, and that's essentially all that we're doing here, multiplying it by that fancy form of 1. Now when we do that, if we go ahead and FOIL this top, we end up with the limit as x approaches 0 of, we'll go ahead and switch colors, the square root of x plus 2 times the square root of x plus 2 just comes out to be the square root of x plus 2 quantity squared, because essentially you're multiplying it by itself. Likewise, when you multiply our two outsides, we end up then with plus the square root of x plus 2 times the square root of 2. And then when we multiply the insides, we end up with minus the square root of x plus 2 times the square root of 2. And then lastly, we end up with minus the square root of 4. Because 2 times 2 just gives us 4. On the bottom, I'm actually not going to go ahead and distribute that x in. All right, we're just going to have x still times the square root of x plus 2 plus the square root of 2. And if we look carefully on top, we have the square root of x plus 2 quantity squared. Well, essentially what will happen is that square root will just end up canceling out with that squared term, leaving us just that x plus 2 that was underneath. Now we've got the square root of x plus 2 times the square root of 2, but we also have a negative square root of x plus 2 times the square root of 2. So those will just actually end up dropping out altogether. And that's actually kind of the whole reason why we use multiplying by the conjugate, to kind of see that actually happen right there. And then we have minus the square root of 4. Well, the square root of 4 is just 2, so we have minus 2. Notice we have no square roots at all on top. And that, again, is the power behind multiplying by conjugates, like we saw with this particular problem. On the bottom, again, we still have x times the square root of x plus 2 plus the square root of 2. So things are still looking kind of ugly on the bottom, but that's okay, because the bottom is actually not affecting our limit and giving us that 0 on the bottom. So we're actually okay with that. Now, on top, these 2's end up just dropping out, so you just have x on top. And also we have an x on the bottom. So those can also cancel out. So ultimately, we end up then with the limit as x approaches 0. Since there's nothing left on top, we have a 1 on top over that square root of x plus 2 plus the square root of 2. Now, again, before that 0 was giving us the issue, so now that it's canceled, we can go ahead and use that direct evaluation. Once we do that, we actually end up then just with 1 on top over the square root of 0 plus 2 is just 2 plus that other square root of 2. So then we end up with 1 over 2 square root of 2's. Now, you may or may not recall, but in math, there is a little rule that says you can't ever have this square root on the bottom. So one way that we can get rid of that is going ahead and multiplying, doing that foo again, of the square root of 2 over the square root of 2. So it looks like we end up with root 2 on top over 2 root 4. So then this will just simplify out to be the square root of 2 on top over square root of 4 is 2 times 2 will just be 4 on the bottom. For me personally, I'm actually okay with this. You did not have to find this one, but if you went ahead and did that, it's probably just good practice. Again, though, that is example 3 and the theorems behind them and assisting us.